Thank you for joining us today. Today I will be presenting salient points from our final report on the technical research on the power and non-power applications of natural gas. I am joined by my co-fellows, Sir Bemboy Subosa and Ma'am Thea Baltazar over Zoom, and our technical advisor, Engineer Melit Villanueva over there at the back. I will present summaries from our technical report on 4 aspects. First, the inventory of power applications. Second, we have the group of technical researches on the power, industrial, and transport applications of natural gas. I will also summarize a few recommendations that we discussed at length in our report. So let's start with the first aspect, which is the inventory of power applications. Our goal was to identify processes in the 2 power applications and list equipment for each process. The inventory has identified 3 types of power generation. Key processes for the 2 types, which are the simple cycle and the combined, were listed and compared, and specific technologies for key equipment were also tabulated. On the screen, we summarize the comparison of the different types of power generation in a table, a portion of which is shown. We identified key characteristics for each, their capacity requirement, working fluids, typical efficiencies, the type of thermodynamic cycle, and typical operating conditions. Common natural gas power generation technologies include the simple cycle, combined cycle, and reciprocating engine power plants. We highlight in this slide the information on simple cycle and combined cycle because of not only, information on simple cycle and combined cycle plants. Simple cycle power plants burn natural gas and air to generate hot exhaust gases that drive turbines. The gas turbines in these plants must operate at lower exhaust gas temperatures to achieve higher efficiencies. Combined cycle power plants, on the other hand, use 2 turbines, a gas turbine to harness energy from hot combustion gases, and a steam generator turbine system to recover waste heat and generate additional work. A combined cycle setup would usually favor higher exhaust gas temperatures so that the second section of the plant recovers enough heat to operate efficiently. Combined cycle plants are established power generation technologies with efficiencies as high as 60%. This is because of not only the power produced in the first cycle that uses a gas turbine, but also the heat recovery that occurs in the second cycle. Hot exhaust gases from the gas turbine are used to generate steam, which can drive a turbine to generate additional power for the plant. In addition to our discussion of gas-fired power plants in the technical report, we also discussed the processes involved in an LNG import terminal. We show here the typical process for an onshore receiving terminal. The LNG from the LNG ships is unloaded using pumps to the unloading arms on the jetty. The fluid is pumped to the storage tank through the unloading lines. And as it is transported through different terminal components, the temperature of the fluid increases. Additional heating is provided by direct fired heaters or heaters that utilize seawater, heated water, or air. In this process, LNG is transformed into gas or regasified, and the natural gas is delivered to distribution pipelines to the end consumers. In our report, we compared the different types of LNG receiving terminals in a table. The one shown on the screen right now is a sample of this. We identified key characteristics, typical capacity requirements and dimensions, and additional information, if available, on the economics and import and export limits. We now move on to the technical research on the power applications of natural gas. So we discussed 2 aspects. The first one is a thermodynamic analysis of gas-fired power plants, and then followed by some key points on decarbonization in the power generation sector. Let's now discuss the first component, Thermodynamic analysis uses the principles of the first and second laws of thermodynamics to calculate the efficiencies of a plant and identify which sections process improvements can be implemented. So I might sound a bit technical at this point onward, but I'll try to at least laymanize these ones for you. Let's look at this illustration of the concept. According to the first law of thermodynamics, energy is conserved, as is mass, of course. The energy in and energy out arrows, which are on the exterior ends of the illustration, are of equal length, which means that the total energy going in and out of any process should be conserved. But energy is conserved only quantitatively and not qualitatively. That means that the quality of energy degrades as it enters and leaves a certain process. So we manifest this energy quality or the usefulness of energy as what we call exergy. You can also see the arrows in the diagram that are labeled exergy in and exergy out. So these are the arrows interior of the illustration. Unlike energy, exergy is not conserved and in fact gets destroyed during a process. Hence, the difference in length in the exergy arrows. This means that the quality of energy available to produce useful mechanical work changes and in fact degrades. So our goal in this component is to summarize what process insights can be obtained from conducting energy and exergy analysis on power plants. And here are a few of those insights. Our research showed that, first, thermodynamic analysis can be used to identify strategies that can increase plant efficiency and reduce irreversibilities in gas-fired plants. And reducing irreversibilities mean maximizing the ability of the thermal plant to produce power. A common factor for all exergy studies is the identification of the combustion chamber as the most efficient process in a combined cycle plant. Thus, performance improvement strategies could specifically target this section. Before we present insights on decarbonization, we first present some typical economic values on conventional power technologies. In terms of capital costs, nuclear has the largest capital cost, followed by coal. Single cycle and combined cycle are the cheapest. Gas technologies are also among the lowest in capital cost when compared to renewable energy alternatives. However, with recent improvements in the operation efficiency for renewable energy, the cost is seen to decrease and converge with conventional generation technologies. We also reviewed literature on levelized costs of electricity of single cycle and combined cycle power plants. The levelized cost of electricity, or LCOE, is a cost per kilowatt hour of electricity generation over the course of operation of the project. We can use this metric to compare various electricity generating technologies of different capacity factors, economic life, fuel costs, and capital cost. We show here a table comparing LCOE values from different organizations. In all cases, the LCOE of a combined cycle plant is lower than that of a single cycle. We can also see from the figure that combined cycle power generation offers a more cost-effective option at par or even cheaper than that of conventional coal. Operating existing conventional fuel technologies are also still more economical than building new power plants. Natural gas has recently been touted as transition fuel, which means that it can be used to support energy transition to a zero carbon mix. Power generation from natural gas is reliable and can balance the intermittency of renewables. It is also the cleaner fossil fuel option compared to coal and crude oil. When used in stationary processes such as power generation, combustion of natural gas releases the lowest amount of CO2 emissions per terajoule of heat generated. One way of determining emissions and the sustainability of the power sector is by implementing LCA, or life cycle analysis. LCA is a technique for assessing the environmental impact of a product or a service. It uses the concept of the life cycle, where different phases denote the stages of product development, manufacture, use, and disposal. As you can see from the diagram on the screen, conducting an LCA will result in an inventory of raw material inputs, emissions, and impacts from every stage. LCA can be used to identify environmental hotspots in a product's life, where environmental impacts are the greatest. Once we know these hotspots, strategies can be devised to reduce their environmental impact. One study we found compared the life cycle greenhouse gas emissions. Example of greenhouse gases are carbon dioxide and methane. So greenhouse gases, also commonly shortened as GHG, are gases in the Earth's atmosphere that trap heat. The increase in anthropogenic or man-made carbon dioxide emissions have been shown to be directly correlated with global warming, as some of you may have already known. This diagram on the screen shows the life cycle GHG emissions for different methods of electricity generation. Coal-fired power plants emit the highest amount of GHGs, and of all the fossil fuel plant types, gas-fired power plants emit the lowest amount of greenhouse gases. Performing a life cycle analysis for combined cycle plants revealed that the highest emissions are generated and released during the plant operation stage. Significant emissions could also occur during gas transport, such as shipping, because of certain methane leakages recorded in the past years. Emission reduction strategies should target the processes in these stages. For example, improvements could be introduced to the regasification and receiving process, or measures could be implemented to improve the thermal efficiency of the power plant itself. One strategy to decarbonize the power sector is fuel switching. It is the substitution of one fuel with another in an industrial process. Coal to gas, or C2G, fuel switching has been shown to be effective in reducing GHG and pollutant emissions. A study in Mexico estimated the reductions in atmospheric emissions when fuel oil was switched with natural gas for a power plant in central Mexico. Significant differences were found for most criteria pollutants, especially sulfur dioxide, or SO2 emissions. This is because natural gas has a relatively lower sulfur content than other fossil fuels. Unfortunately, on the downside, the study also determined that there are no significant differences for carbon monoxide, or CO, NOx, and carbon dioxide emissions when switching to natural gas. This is because of the lower heating value of natural gas, and that means that a larger volume of natural gas would have to be combusted to generate the same power offered by fuel oil burning. A workaround in this concern is to operate high-efficiency gas-fired plants or to adopt carbon capture and storage. There are other decarbonization strategies available for the power sector that we have outlined in our technical report. Since natural gas is touted to be a transition fuel, efforts must also be exerted to streamline the transition to a zero-carbon future. However, emissions from upstream processes could outweigh the low-carbon benefit of natural gas use. Hence, additional mitigation strategies should be implemented. We see a few examples of these strategies on the figure on the slide, such as implementing measures to increase thermal plant efficiency, adopting carbon capture and storage techniques, and promoting short-distance transport. And that ends our discussion for the technical research on the power application.